In the first part of the compression chapter, we talked about how to exploit character frequencies. In this next part, we will talk about repetitive parts in the text and how to exploit this. And we will see the Lempel-Ziff methods as one core representative of this family of compression methods. So it turns out that many natural texts have a certain type of redundancy that is not well reflected by character frequencies. Here I listed some example of a text that might not be the very most natural one, but it's definitely a very repetitive one. But if you were to count how often the characters occur in this text, you will find that it's not that unbalanced. In a sense, if you make this very, very long, then all the characters will occur roughly as many times as if you were just looking at the first copy of this sentence. And that's a standard English sentence with no bigger redundancy than usual. So we would essentially pay the cost of the number of copies times the cost for storing one copy. Well, in fact, the text is just the very same sentence over and over again, pages over pages. So that doesn't seem to capture the redundancy in this case. Character frequencies are just not seeing this type of long distance redundancy. And we'll see this often in natural language text, but also in other types of data. DNA sequences tend to have the same type of long range copies or almost identical copies. And character frequencies don't capture this. In a sense here, what we would like to do is go away from character encodings. As long as we're encoding every character in isolation using the same code, there's no chance we will capture this sort of redundancy, of repetition. As a first method, a first simple method that falls into this category, we'll look at run length encoding. For two reasons. One, because it's the easiest method that does exploit repetitiveness in a certain way, even though only in the simplest form. But also it is another building block that for modern day compression, you usually don't rely on a single method, but you chain things together in an interesting way to squeeze the last little bit of redundancy out of data. And run length encoding is a fundamental part in the bzip pipeline that we will look at the end. So let's see what this is about. A simple form of repetition is the same character repeated many times. And an obvious application of this might be a black-white scan of a text page, say, where you have some text. You can hopefully see this. If you were to represent each pixel by a single bit, for just black-white, that's enough, not grayscale, black-white in the literal sense, you would expect to see many runs of zeros for all the background, and maybe even runs of ones, because the resolution of the scanner is much higher than individual widths of the characters, of the glyphs. So you expect to see many runs of repeated characters in such an application. And run length encoding is brilliant for picking these up. Indeed, we will restrict our attention for this unit here, for this subsection, to just a binary source alphabet. Already for Huffman coding, we were restricting attention to a binary coded alphabet, but now we'll assume the same for the source alphabet. Just to make our life a little easier, you can generalize the ideas to larger alphabets, but indeed it's often used on binary inputs anyways, because as I said, it's used not as the first step, but after other methods have already done their magic. So a simple example of run length encoding here, is if we have this input text. So I just want to illustrate the idea. The first step is we parse this input text into phrases, which are just runs of the same character, right? Okay, so here we have 5 times the 0, 3 times the 1. So we would always group these together. As long as the same character repeated, it's the same phrase. That's something that that we will use in this section. A phrase is a part of the source text that we encode as one step. So we have to encode these phrases, and well, obviously for a binary alphabet, it's enough to store what was the first bit in the source, 0 or 1, and then what's the length of each subsequent run. We don't have to store which bit it is, because runs have to alternate between 0 and 1 if the alphabet is binary. So in our example, we would write a 0 for we start with 0, and then 5, 3, 4 is the length of these runs. There's 5 zeros, 3 ones, and 4 zeros again. These 4 numbers completely specify this source text, and that one has, well, what is it, 12 bits, and this might be, hopefully, be represented in fewer bits. So that part of run length encoding is very easy. The question that remains is, how do we encode these run length numbers, which can be arbitrary integers, in binary? For that, we have to think a little. And to get you started, I'd like to ask you to think more generally. How would you approach this problem of storing a string? Think of your favorite programming language. It probably supports strings. It would be a really weird language if it didn't. And probably these strings can be as long as you wish. You can specify a string of arbitrary length as long as it fits in memory and blah, blah, blah. But there's no built-in limit usually for the length of a string. How does such a language represent an arbitrarily long string? At the end of the day, it has to reside in main memory. It has to be stored in your computer. So you have to have some way of encoding it in binary. And that's the same question that we're asked here in run length encoding. We have arbitrarily long integers. At the end of the day, these are binary strings, so it's the same problem. How can we represent a string that can be arbitrarily long if the only thing we have is a large binary memory where we have to store things just using zeros and ones? Think about it for a second, and I'd like to see a few more answers. Maybe you can help me out and type something. Think about your favorite programming language. All programming languages have found a solution for this. So they all have solved this problem. Maybe you wondered sometime before how they do it. Let me show what people came up with so far. The first suggestion is a linked list. You could use a linked list indeed, provided that memory management is there for you. A linked list essentially solves the problem by reserving a pointer for each bit in the extreme case, or for each character. And you would have a special symbol that says this is the null pointer, right? That says there's no more next character. That's a way to do it. It would be inconvenient in this case because it takes a lot of space to store all the pointers. It is true that we can assume the length is a multiple of 4. If we store the length in bytes, or well, bit strings whose length is by definition a multiple of 4. Why would every bit string have a length multiple of 4? Anyways, you could make that assumption. My claim is it doesn't make the problem fundamentally easier if you have this restriction. Linked lists are great, guys, but they're very space inefficient because you would need a way to store pointers. And that pointer needs as many bits as you have space in your entire memory. So that really grows beyond any bound. Using graphs, sounds like you use pointers unless you get more specific. It probably has the same issue that pointers need a lot of space. I'm not sure how KMP helps. In chunks and join them. That's a good engineering trick. Instead of using linked lists for every character, you definitely want certain chunks of a certain length, and you could use pointers again. But remember, if you don't know any upper bound on the length of the thing you store, pointers are a problem. Variable sized arrays, that sounds good, but how would you do that? A string of arbitrary length is, in a sense, an array of arbitrary length. How do you store an array? How do you store an array of arbitrary size? So maybe keep thinking about this a little more. It's sometimes fun to think about these very fundamental problems that obviously have many good solutions because we use these solutions all the time. All right. I'll tell you a solution for the special case that we need. And we can revisit the other more general question. I can tell you what the solution is in Java, for example, if you're curious. What we need here is an encoding for integers. So we don't really need 0, so we can start at 1. But we need the encoding to be prefix-free so that we can represent all possible integers, and we can decode that unambiguously. That's the key thing. The challenge is to know when to stop reading. Well, that's same thing as saying prefix-free. If it has to be prefix-free, it must be obvious when you have to stop reading. So how could you do this? There's a very simple solution, which I'm sure, well, this is not what you would come up with, but it's actually very simple. You can obviously do this. You'd use the unary encoding, which means to specify a number, you write as many zeros as that number is, finished by a single 1. That's a great encoding. It works. It's just super, super bad in terms of space, right? It takes as much space as the number is big. And you could actually represent 30 with just, 5 bits, and now you expanded it to 31 bits. And, well, we started with run length encoding to get rid of long runs. Now to store the runs, we produce long runs. Maybe this is not the solution yet. But we still build on this. And the trick is to see this as the base case of a recursive construction. Not sure if this is helping you. The standard binary encoding of numbers is actually fine. It's actually very efficient. The problem is that it's not prefix-free, right? If I write 101, you don't know if that means 5 or it's actually the prefix of an even longer number like 10. But the encoding itself is space efficient. So what we'll do is we'll store the length of the binary representation in this stupid unary encoding, which is space inefficient but prefix-free. And then append the binary encoding. Now that we know how long it is, it's no longer ambiguous. Okay? That's the key idea of Elias gamma code. Once you start thinking about this, you immediately find that there's some obvious ways to improve upon this. First of all, the length is always at least 1 bit, so we might not have to store exactly 7 bits here, but we can store just 6 zeros because we never need the 0. That's just not needed in our application. And also the binary representation of any number, if you leave out all leading zeros, necessarily starts with a 1 by definition. Otherwise, you wouldn't have taken all the leading zeros away. So there's no need to store that 1. We can start 1 later. Okay? But that's just minor twists to the core idea, which is store the length of the binary encoding in unary and append the binary encoding. So what that leads to is for 1, The binary representation is a 1, just a 1. The length of that is 1, but we store L minus 1 zeros, which is 0 zeros. So 1 is just mapped to 1. The number 3 is 1, 1 in binary. That's what you see here. The length of that is 2, so we prepend 1, 0, 1 less than 2. One more example, 5 is 101. Length is 3, so we have to prepend 2 zeros. 30 happens to be this. Length is 5, you prepend 4 zeros. There you go. That's Elias gamma code. That's a way to represent an arbitrary integer. It can be as big as you want in a prefix-free way. And as you might see from this, we take the binary encoding and we make it roughly twice as long by adding this bunch of zeros. So the code word length for a number k is log k to represent that number, and then twice, plus minus 1, minus 1 I guess, because of the 1 0 less, and maybe minus 2 actually. But this is roughly what you get, whereas here it was linear. Okay, so that's the important difference. Before we come back to the string question, let's practice this one. Here is a bit string. There are more numbers encoded here, so you're just asked to decode the first integer in Elias gamma code at the beginning of this bit string. I'll show you the code again. You have the bit string in the question. I added more bits to the bit string so that you don't have the obvious separator, so you really have to figure out the encoding. So your answer should be a decimal integer, right? I'm asking you to decode. So this should be, again, a number in capital N in the natural numbers. So don't send me the bit string. You want to decode that further. Okay, you might need a second to do this. And we'll go through an example after that together. Okay, lots of suggestions. Let me show you some of them. Okay, maybe let's just go through this together. Or I'll leave the question open and just go through the examples, and then you'll try again if you haven't done it yet. So let's see some examples, and you can work out on the other one on your own. First, an example for encoding, and this is the full run length encoding now, which uses the gamma code for storing the run lengths. Okay. So, but you'll see this involves lots of practice examples of gamma code. So it works fine. We have this long bit string. We start by first noting what is the first bit, 1 or 0. Well, it's a 1, so we store this. Next, we store the run length, and this is 7 bits. So how do we store 7? Well, 7 is 111 in binary. The length of that is 3, so I have to add 2 zeros in front. And that is what has happened here. That's the 7. The next run has length 2. The 2 is 1, 0 in binary, prepend a 0. That's what you see here. Another one, we have just the 1. So we remember that was just mapped to 1. Maybe we don't have to do that one again. Okay, good that I already counted this. 20 zeros. Now, 16 and 4 makes 20, so that's 20 in binary. And adding 4 zeros in front gives you the code for 20. And another one, 11 ones at the end. 11 is 8 plus 2 plus 1. So it's a 1, 0, 1, 1 in binary. And adding the 3 zeros to code the length gives you the result. So that is the coded text for run length encoding of this bit string. That's the entire method now in its full glory. Let's see how well this worked. If you count here, that was 26 bits in the coded text and 41 in the source text. So that's down to 63%, which looks great. But also, of course, this was a fairly favorable example for run length encoding. Now let's practice some decoding. And again, this is a run length encoded bit string. So it will follow the same pattern. The first bit is telling you what is the first bit in the source text. So it's a 0. And now we have to start reading the next number. So what you do is you look for how many zeros you find. In this case, there's 3 zeros, so the length of the binary representation of the run length is 4 bits. So you take the next 4 bits and decode that in binary. Okay. That happens to be 13, 8 plus 4 plus 1. So you know you have the 13 is the encoded number. And so you write 13 zeros in the decoded source text. Okay. And then you continue with the same procedure. You count how many zeros do you find. That's 2 plus 1. So you have to read the next 3 bits and decode that as a binary number. That is 4. So you append 4 ones. Okay. One more time. You start, how many zeros do you find? Well, no 0. So you just read 1 bit. That's a 1. So it's 1. The next run length is just a 1. So you append 1 of the next flip bit, which is 0. And one more time. You count the number of ones. There's the number of zeros. There's 1 0. So you read the next 2 bits. That's a 2. So you append 2 more ones, and that's it. Okay. Do people want to go back to the example from the question? So let's do this one more time here together. This is not run length encoding, so there's no leading 0, 1. It's just numbers. So we count how many zeros we find. That's 3. So we have to read the next 4 bits as binary number. That's these 4. That's a 1 plus a 4 plus 8. That works out to 13. So 13 is the correct answer. I see people need more practice for this. I know this is really, really, maybe you want to see these, but I'll lock it. I know this is really, really detailed stuff. You will have more opportunities to practice. Good. Let me see if I can jump over some of the many slides for this example. Good. So that is run length encoding. It's okay. I thought I had some pseudocode, but maybe it's not needed for this one. You can extend run length encoding to larger alphabets, but then you have to say what is the next character that is repeated. For binary, you didn't need that because there was only one other character. It's actually used in some older formats for images, especially for scans. But again, as I said, in isolation, this is not the method of choice. You usually use it as part of a larger pipeline of compression methods. It is simple. It's also fairly fast. In the best case, it achieves remarkable compression from n bits down to log n bits, roughly, factor 2 or so. But this only happens if you have very few runs, very long runs of the same character. But this is the potential gain from run length encoding is much, much bigger than what we've seen before with the character encodings. There's no way you get sublinear with any of the character encodings, whereas with run length encoding, you could potentially get exponentially smaller. However, for typical types of data, if used in isolation, it doesn't really give good compression. You need, if you work out exactly how many bits you need to encode the numbers with Elias code, you will see that if the run lengths are not bigger than 6, then you don't get any compression. And you actually get worse. You get expansion whenever you have runs of length 2 or 6. These happen to be the two numbers that are represented with more bits than necessary. Or more bits than the unary encoding in the original source text would have taken.